Hello and welcome to Project 152, your weekly specialist exam prep. Now, every week we go through questions from the QCAA. If you stick with us for the whole time, you'll have done every single one of the 152 questions that the QCAA has ever done. Now, this week is week 23. We're going tech active, so make sure you've got your calculator with you. Let's get started. So a fun one here, we've got some matrix algebra. We have a matrix times x times a matrix is equal to this matrix. Now, in order for us to figure out what x is, we need to isolate x. Now, I'm just going to give all of these matrices a letter, A, B, and C. And because I've got it written out like this now, I'll just write it as a matrix equation, which is A times x times B equals C. That's what this says. A times x times b equals c. And now I need to get rid of the a from this side, and I need to get rid of the b from this side. Now I'm going to be shortcutting a little bit, but hopefully it makes sense. We're going to bring the a from this side to this side. Now notice the a is before the x. We call this pre-multiplication. So when we bring the a to the other side, we need to make sure that it goes on the left-hand side of the c because we're pre-multiplying it. X, B. Now, when we bring that A over, it becomes an inverse. So we need inverse of A, C. Okay, now notice this B here is after the X. When we bring this B over, we're doing something called post-multiplication, so it has to get tacked onto the end. We have X equals inverse A, C, and then inverse B because we brought the B to the other side. Now that I have a single equation, x equals this times this times this, I can type it into my calculator, spit out an answer. So here's my calculator. It can get confusing. A lot of people will want to press this one and enter it in here. You can do that, but I prefer clicking the math button. That's where I enter almost everything. So entry here, and then when I click this mat vector button, it does something different. It does this. Now, what do I want? I want inverse of A. So I need a 2 by 2 matrix because A is a 2 by 2 matrix and A is 0, 1, 2, 3. I want the inverse of it, so I can just raise it to the power of -1. That's how our notation goes for that. Now I need C. Okay, so let's put in another 2 by 2 matrix and C is 8, 9, 0, 0, 1. And then I need another matrix, and that matrix is 4, 5, 6, 7, but another inverse -1. Now I think I need multiply signs here. I don't think it's going to work if I don't put those multiply signs in there, so I'll put those in there now. Okay, done, enter, let's go, execute, single answer, 3, -4, -1, 2. Do I have that answer here? I do. The answer is B. All right, great stuff. Celebrate. Next question. So it is a confidence interval question here. Lots of words here, and there is a distractor, a number here that you just don't need, but they're putting it in there to see if they trick you. All right, so what does it say? Time taken, blah, blah, blah. A researcher claims that the population mean is 8.2 minutes. The mean time taken to complete this test by a sample of 10 of these students is 8.1 minutes with a standard deviation of 1.2 minutes. The 95% confidence interval is... We can use our calculator for this 100%. We don't need to write anything down at all. Now I'm in stat mode on my calculator here. I'm going to click intervals and Z. Okay, and now I'm doing a sample. So one sample here. Okay, let's see what we've got. Data, variable, good. We're looking for a 95% confidence interval, also good. Now, what about standard deviation? 1.2 minutes. Okay, good. Now, what about the mean? This is where they're trying to trick you. Here, they've got a population mean of 8.2 and they've got the sample mean of 8.1. When we're doing this question, we need the sample mean. We're calculating our confidence interval using our sample mean, so 8.1. We're never going to use 8.2. That's the distractor. All right, what's our sample size here? Sample of 10, go. Okay, and then we calculate, and we get 7.36, and we get 8.84. Do we have that answer? Yes, A. A nice easy one, a little distractor there. Keep your wits about you. celebrate, next question. All right, so we've got a question here. We're determining the momentum of the object. Now, momentum doesn't appear on your formula sheet, so it's one of those formulas you need to know. The momentum formula is this. Momentum, P, is equal to mass times velocity. So let's just write that down. Momentum equals mass times velocity. And we're trying to calculate the momentum at a particular time. Okay, what's the mass? The mass is 4 kilograms. And what's the velocity? It's here, 9 plus 8t minus t squared. So 4 times 9 plus 8t minus t squared. Okay, so far so good. Determine the momentum of the object when t equals 3. So I'm going to let t equal 3. And I'm going to plug this into my calculator with t equaling 3. Notice that I could expand these brackets and things like that, but I'm putting it into my calculator, so I'm not going to do that because I could make a mistake there. Let's just put it into our calculator exactly as it's appearing. So here I've entered it in my calculator. I want to show you that I'm doing this in a way, and I'm checking my answer to make sure I'm not making a mistake. 4, okay, I wrote 4 down the start, and I've got those 2 brackets around it, and then 9 plus 8 times t, 3. So notice that I've put the 3 in brackets. That's really important because you might end up doing something strange here. If you don't put the 3 in brackets, you might end up with like negative 3 squared or something like that. We don't. We want minus 3 squared, which is different. Okay, executing, we should get an answer. 96 is 96 on our answers. It is. The answer is C. A fun little one. You are not going to have access to that formula, so make sure you've got it memorized. That's momentum. There's another one for force that you'll also have to memorize. Fun question. Celebrate. Let's go. So this should be a short and sharp one. We're determining the gradient of the tangent to the curve this at this point. Now you'll notice this isn't a function, this is a relation. We're thinking implicit differentiation. So y squared minus 3x equals 5. So let's take this implicit differentiation. We've got this y squared here. The derivative of y squared is 2y, but because it's with respect to y, we need dy dx here. This next one, the derivative of negative 3x is negative 3, and the derivative of 5 is 0. We can rearrange this a little bit by bringing 3 to this side, which means that dy dx equals, dy dx 2y equals 3. And then we can divide by 2y. We get dy dx equals 3 over 2y. Now this is an interesting question because the derivative depends solely upon y. X is nowhere to be seen. So when we sub in this point, we're not just subbing in this point, we're just subbing in the y value 2 root 2. So sub 2 root 2 in here for y, and then just type that into your calculator. You don't need to watch me do that. My calculator says the answer is 0.53, and I can see that up there. The answer is B, celebrate. So we're doing confidence intervals again here. Blah, 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 lifespan, and we're given the confidence interval. We've got a 95% confidence interval, and these are our 2 values. Part A, it's worth 1 mark. Determine the mean lifespan for this sample of batteries. All right, so we've got a confidence interval. Let me just draw that as a picture. So there is our confidence interval. We're looking for the mean lifespan for this sample of batteries. Now, the mean comes right from the middle of our confidence interval. You should remember our confidence interval formula. To find our lower and upper bounds of our confidence interval, we're adding something to the mean, we're subtracting something from the mean. So the mean is this middle value right here. Now, how do we find the middle between 2 numbers? We add them together and we divide them by 2. That's it. Add them together, divide by 2, we get 2,372.5 hours. That's that number right there. All right, let's celebrate that one. Now we are going to move into part B here. Now I think I need this to answer part B, but I am going to get rid of the rest. Let's regroup. All right, so that's a little bit of answer from part A we needed. Let's look at part B. The standard deviation of the lifespan of batteries in this sample is 125 hours. Determine N, determine the sample size. This is a classic because it uses this formula, right? And there's something we don't know. The thing we don't know is n. We know everything else, or at least I think we do. Now, when it comes to this kind of question, you've probably just got to choose one of these, either the lower bound or the upper bound. I'm going to choose the lower bound here, and let's look at what our lower bound is. 2321.4. Okay, 2321.4, that's our lower bound. And the formula for finding the lower bound is, you can see here, sample mean, x bar. So that's 2372.5 minus the z-score. Now, 95% confidence interval. So we should know a z-score for a 95% confidence interval is 1.96. S is our standard deviation, our sample standard deviation, which we were just told is 125. So multiplying this by 125. And then we have here root n, and that's the thing we don't know. So we have a nice formula now. Number equals blah, 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 root n. Root n is the only thing we don't know. Tech active question. So I'm going to solve using my graphics calculator. Let's get our calculator out, solve it. So the hard part here is just remembering how to do this on your calculator. We click option if we want to do some kind of calculation. So option and then calculation. And the thing that we're doing is solve n. So we're going to ask it to solve our equation for us. I'll just close up those brackets and then I just type in this whole equation here. Instead of n, I'll write the letter x. Let's just double check that I've done it right. Solve n, 2321.4 equals 2372.5 minus 1.96 times 125 over root x. Okay, executing that. It always gives us this little warning here, and there might be two answers. Gives us one answer, 22.98. So n is equal to 22.98. Now you can't have a sample size of 22.98, so you have to say that the sample size is approximately 23. Now, if you've done questions like this before, you've got some experience with it, you might think, oh wait, 22.98, is this one of those trick ones where you have to like round down to make sure that you have at least this confidence interval or something like that? No, this isn't one of those trick ones. You just round normally here. Now, why is this not one of the trick ones? It's because we're told that there's a 95% confidence interval. We're told this is the 95% confidence interval. We're told everything about this. So that 22.98 is not a result of being like just enough or not quite enough. It's simply a rounding error. There should have been more decimals here and we would have got exactly 23. All right, celebrating, and we're on to the last question. Now, the last question here, it says, use the result from question 12b, so n equals 23, to explain whether the assumption that the lifespan of batteries is normally distributed is required to support the supervisor's calculation. All right, so this part C here is testing your theoretical knowledge of the central limit theorem. So, the central limit theorem says that it doesn't, for large enough samples, that's important, for large enough samples, it doesn't matter whether the population is normally distributed or not. For large enough samples, the distribution of the population does not matter. The distribution of the sample means will always be normally distributed. Okay? However, for large enough sample sizes. Now, by convention, n equals 23. That's not a large enough sample size. You really want a sample that's larger than 30. Let's look at my pre-prepared solution. Yes, the assumption is required. We have to assume that the population is normally distributed. Because the sample size is less than 30, the distribution of the sample means cannot be assumed to be normal unless the population is also normally distributed. So if our answer here was different, if our answer here was n equals 45, our answer here would be different. Our answer here would say, no, the assumption is not required because n is greater than 30. So 30 is your magic number here. If it's less than 30, you have to know that the population is normally distributed or it won't work. If n is greater than 30, it doesn't matter how the population is distributed. your sample means will be normally distributed. Celebrate! So we've got an interesting question here. It says an object is moving in a straight line with an acceleration represented by this differential equation. What are we doing? Determine the general solution of the differential equation. All right. Now, in this case, you don't really need to worry about is it acceleration, is it velocity, what's happening. They're asking for the general solution of a differential equation. So this could be the rate of any kind of change. It wouldn't have to be velocity and acceleration. We just need to figure out how to solve this differential equation. Let's write it down. So this is really ripe for a separation of variables style technique. So I see this dv over here, so I can leave that there. All right. This dt, I'm going to bring to the top on this side. I'm integrating both sides here, right? Now this 4 plus v squared, I'm going to bring to the bottom here. So it's going to be 1 on 4 plus v squared. And then on this side, what I'm left with is the negative 1. Done. Awesome. And we move from here. So separation of variables, if that didn't make a lot of sense, you want to go and check out your separation of variables stuff. Okay, what next? Well, we just integrate both sides. Now, I know I've got a formula for things that deal with these, so we'll deal with that one in a second. This one, however, feels relatively straightforward. The integral of negative 1 is negative t, right? Why t? Because we're integrating with respect to t. So with t, and then a little plus c on the end. All right, let's find our formula for this and then we'll deal with it. All right, so I had a look at my formula sheet and I'm coming to this one. This is going to be nice. Now, you can see that they don't quite match, right? Because this is 4. Now, 4 is supposed to be a squared, and then whatever's on the top is supposed to just be a. In other words, whatever's on the top, we need to square it to have it on the bottom. So this is a 1, but it really should be a 2. It should be the square root of 4. So how can I make it so that it's a little more like that? Well, if I multiply the whole thing by 1/2, I can now multiply this side by 2, because 1/2 times 2, that's equal to 1. So if I multiply by 1/2 out the front and multiply by 2 inside the integral, I haven't done anything. I've just multiplied by 1. So that's going to give me 2 over 4 plus v squared with respect to v. And now this perfectly matches this formula. So we can say that it's going to be equal to 1/2 times inverse tan and then x over a. Silly me, not x over a, v over a. And a is 2. Okay, I think we're done there. We've got a nice little formula here. You can see the plus c on the end, but we don't need the plus c because we already have an arbitrary constant on this side. We don't need one on both sides. So I think we're done here. This is a general solution of the original differential equation. Good job. And now we can start on part B. So what does part B say? The initial velocity of the object is 1.5. That's interesting information because that'll allow us to find c. Determine the time when the particle comes to rest. Okay, so let's deal with the actual question in a second, but we can see that we've got an initial condition. So let's sub it in and then solve for c. So if sub t equals 0 and v equals 1.5, it's obviously silly having negative 0 plus c, it's just c. Type it into my calculator and I get c equals 0.32. Notice I'm in radians mode. You'd have to have a very good reason to put yourself into degrees mode. c equals 0.32175. Let's go with 0.32. So now that we know that c equals 0.32, we have an equation. Half inverse tan v on 2 equals negative t plus 0.32. Let's answer the question. Determine the time when the particle comes to rest. When particles are at rest, they have velocity equals 0. So we just need to let v equal 0 and figure out what t is at that velocity. All right, so I've let v equal 0. Here's my equation. Now, if you type this into your calculator, you'll get 0. So that means that 0 equals negative t plus 0.32, which of course means that t equals 0.32. And that is our final answer. What have we got? T in seconds, 0.32 seconds. That is when our particle is at rest Final answer, done, celebrate. So this is a real doozy of a question, and if you're not familiar with these kinds of questions, it can be really hard to know where to start. So let's look for some hints. Consider the identity, and here we have an identity, okay? Determine the values of A, B, and C using de Moivre's theorem. Okay, so there's our hint, using de Moivre's theorem. So there's our formula, de Moivre's theorem, and I'm looking at this, and I'm seeing cos 4 theta, and I'm looking at this, and I'm seeing cis. So it's a little bit confusing, cis, cos, how are they related to each other? So let me write de Moivre's theorem, and instead of writing cos 4 theta, I'm going to write cis 4 theta. Let's see what happens. So if I write cis 4 theta, we know from de Moivre's theorem that that can also be written as cis theta to the power of 4, right? That's what de Moivre's theorem does. If you want to raise a complex number to the power of 4, you can write it as cis 4 theta. Okay, and now let's stop and think for a second. What does cis actually mean? What is it? Cis means cos theta plus sine theta I. And in this case, we're raising it to the power of 4. And now we're kind of in business, right? Because we've got this cis theta 4 is equal to cis 4 theta, but it's also equal to cos theta plus sine theta I, all to the power of 4. And maybe if I expand that, I'm going to get closer to something like this. So expanding this feels like a little bit of a pain unless you look at your formula sheet and you realize that what you're dealing with is a binomial theorem, x plus y to the power of n. So now we just do exactly what this said. Now I warn you, this is going to get a little tricky, but we're going to go for it. I'll just make some more space here for myself. We'll switch colors so it's very clear what we're doing. Our first term is just x to the power of n. So it's just cos theta, this is our x here, to the power of n, which is 4, cos 4 theta. So far, so good. Now, our next term is n1. So 4 choose 1, that's 4. So 4. And then it's x to the power of n minus 1. So x to the power of 3. So cos 3 theta times this, which is sine theta I. Okay, so far so good. It does get a little more confusing now though, because I'm going to write plus here, but it's going to change soon and you'll see why. All right, the next one is going to be 4 choose 2, which is 6. Okay, and then we've got this cos squared theta. All right, because the powers go down for the x's and they go up for the y's. So our next one, we need to raise all of this to the power of 2. So let's think about what that means. Sine theta I squared, right? So that means that we can square this and we're squaring this as well. Now the square of I is -1. So it's going to be equal to -1 times that. In other words, it's just going to be sine squared theta negative, right? So I'm putting a sine squared theta here, but because it's negative, I'm changing that positive to a negative. All right, done. All right, so the next one here, it's going to be 4 choose 3. So that's going to be 4 again. And I'll put a little plus here. That might change. We'll see. 4. And we did cos to the 4, cos to the 3, cos to the 2. Now it's cos to the 1. So just cos theta. And then we run into a little bit of trouble again because we need to take this sine theta I to the power of 3. All right, so let's think about what that is. The sine theta to the power of 3, that's straightforward, sine 3 theta. But the I cubed is negative I, right? So we got the I here, but it's negative, so we get this. So I need a sine cubed theta I here, but that plus does turn into a negative. Now I do have one last term to do, and the last term is just going to be y to the n, y to the n, y to the 4. All right, so that's going to end up being sine 4 theta, and then I to the 4 as well. Now I to the 4 is 1. So I end up with just sine 4 theta plus, so sine 4 theta. Okay, we have done it. We're just about home, really. We're nearly done. So we've got cis 4 theta, we've got cis theta to the 4, and we've got cis theta to the 4 is equal to all of this. This is equal to this is equal to this. Now, look at what the question was. It said cos 4 theta. So let's take a closer look at what's going on here. Let's look at this. This is a real number. Cos theta to the power of 4, whatever theta ends up being, you raise it to the power of 4, that's a number, a real number. However, this is an imaginary number. This, you can see the I there, that's why it's imaginary. This is a real number, this is an imaginary number, and this is a real number. Let's look at the left-hand side. Cis 4 theta, remember what we said that was equal to? Cos theta plus sine theta I. Cis 4 theta can also be written in terms of just cos. Let me get rid of that. Written in terms of cos and sine, we can write it as cos 4 theta plus sine 4 theta I. Don't lose sight, when you're writing cis 4 theta, you're writing shorthand cos 4 theta plus sine 4 theta I. That's what's happening. Okay, this is great news. We're pretty much done now because we've got a real component of cos 4 theta, and we can equate that real component with this, and this. All right, so equating real components. So here we have it. Now we can say that cos 4 theta is equal to cos 4 theta minus this plus this. That's all of our real components. We can just discard our imaginary components because they're equal to that thing there. Maybe in the future they'll ask a different question where they ask about the imaginary components, but this one's all about the real stuff. Okay, I see a bunch of like sine squareds and cos squareds all mixed together. There's probably a lot of different ways to do this, but I think I might just convert all of these sines into coses using my Pythagorean identity. I can just rearrange that as sine squared theta equals 1 minus cos squared theta. So I'm just going to replace that with this, and I'm going to replace that with 1 minus cos squared theta squared. Might be getting a little hard to follow here. Our sine squared theta becomes 1 minus cos squared theta according to this identity, and our sine 4 theta is the same as sine squared theta squared. And sine squared theta is this, and then we square it. So this is equal to that. All right, let me just sort of expand a bunch of this. All right, so there's my expansion. It was this times this makes that. It was this times this makes that. And then 1 minus cos squared theta. That's 1 minus cos squared theta times 1 minus cos squared theta. That's 2 lots of this times this, and cos squared theta squared, which is cos 4 theta. Done. Grouping like terms, so I can see a cos 4 theta there, I can see a cos 4 theta there, I can see some cos squared thetas here, I can see a cos 4 theta there, and I can see a 1. So I can group these 3, and I can group these 2, and the 1 will stay on the end. So you can see, hopefully, that this is very close to our identity up here. We've got cos 4 theta on the left-hand side, cos 4 theta, and here, what do we have? We have 8 cos 4 theta, so we wanted a cos 4 theta, so that's good. Then we have minus 8 cos squared theta, but we wanted a sine squared theta, not a cos squared theta. Luckily, I can fix that because I can replace that cos squared theta with 1 minus sine squared theta. Right there. Okay, I can expand those brackets. There you go, those brackets expanded to be this. And finally, I can group these constants. That's it, we are done. We can say now that cos 4 theta, which is where we started, cos 4 theta is equal to cos 4 theta plus 8 sine 2 theta minus 7 to the power of 4 to the power of 2. Okay, so 8, 8, and negative 7 are our actual answers because it says determine the values of A, B, and C. A equals 8, B equals 8, and C equals negative 7. There is our final answer to part A. Celebrate. All right, we do need to do part B though, which is just state an appropriate method of verifying results from 16A. It's a 1-mark question. It's a very sort of strange sort of question to ask. Let me show you what the QCAA was looking for here. All right, here we go. Here's what the strategy was. A verification strategy would be to graph y equals cos 4 theta. So graph this, y equals cos 4 theta, you'll get some sort of graph. Graph y equals this, 8 cos 4 theta plus 8 sine squared theta minus 7. When you look at those two graphs, they should be identical because this graph should be equal to this graph. So that's the kind of description they were looking for a good strategy to verify that this is true. All right, celebrating that one. Fun question. Well, that's it for another week. Thanks so much for hanging around. It's been week 23. Next week is week 24. We're going back to tech-free questions. Looking forward to it. Catch you then.